Hello, and welcome to our presentation on hydronic versus steam applications. We've seen a lot of designers moving away from steam towards the use of hydronic hot water systems to distribute heat for campuses or large facilities, and many people seem to believe that this is a more modern, efficient way to operate. Steam is sometimes viewed as old-fashioned and inefficient. We'll show you that steam remains one of the most efficient media that can be used to transport large amounts of energy. To do this, we're going to analyze a typical high-temperature hot water system from an actual specification and compare it to a system that uses steam instead of hot water to transport the same amount of energy. Before we get into our analysis, it's important that you understand a few key concepts about modern steam systems. Maxi-Therm has developed a patent-pending high-efficiency closed-loop steam system, which is the key to achieving the efficiencies we will describe later in this presentation. If you haven't already done so, please watch our YouTube video which explains the concepts. Just click the link shown. If you're already up to speed on Maxi-Therm, let's dive right in and compare our ideal steam system to an actual hydronic high-temperature hot water project specification. Here is a layout showing a typical high-temperature hot water system. Let's quickly go through each part. First, highlighted in red, is the main loop piping which extends to all areas of the facility or campus. There, heat exchangers are used to provide building heat, domestic hot water, etc. You can see the supply at the top right and the return at the bottom left. Here are the main pumps that move the water around the loop. Next are the boilers and boiler loop piping highlighted in green. These boilers form the primary loop that supplies heat energy to the secondary campus loop. Here are the individual boiler pumps. Now let's take a look at our real-world example. This is an actual engineering schedule for the boilers, like the one shown in green on the previous slide, which are used to generate the high-temperature hot water in our example system. Note that they are designed to produce 240-degree hot water with a return water temperature of 165 degrees for a delta of 75 degrees. Each boiler is designed to produce an output of 17,570 MBH, and this system is designed to have two boilers running at all times to produce our design heat output of 35,140,000 BTUs an hour. Next, let's take a look at another part of the same specification. On this slide, we see the pumps that are specified for our example project. The pumps used for the campus or building loop are P1 and P2, which are 60 horsepower pumps rated 1150 GPM at 160 feet of head. In this design, one pump runs 100% of the time while the other is the standby. In addition to the loop pumps, we have the individual boiler pumps BP 1, 2, and 3. These are each 15 horsepower pumps rated 700 GPM at 45 feet ahead. As we discussed in the previous slide, the system is designed to have two boilers running to provide our design heat output, so we have 30 motor horsepower in operation 100% of the time. Add those together and we come up with 90 total motor horsepower operating 100% of the time to enable our hydronic system to work. Next, let's analyze the energy it takes to run those pumps. To begin our calculations, we need to determine just how much water flow it takes to deliver 35,140,000 BTU an hour at a 75-degree delta T. We'll use the mass flow equation Q equals mc delta T. For water, the specific heat C sub P equals 1, so we can ignore it and rearrange the equation to get m equals Q divided by delta T. Plugging in our numbers, we can see that the mass flow rate m is 468,533 pounds per hour of water flow needed. Next, we'll convert to GPM. We simply take our flow in pounds per hour and divide by 60 minutes per hour times 8.33 pounds per gallon to arrive at 937 GPM. Now that we know how many GPM our pump has to move, we can calculate how much energy is needed to do that. Pump output horsepower can be calculated by multiplying head pressure in feet by flow in GPM and dividing the result by 3960. As you can see, our pumps need to output 37.88 horsepower to achieve that. Of course, both the pump and the motor have an efficiency that's less than 1, so we'll need some more math to determine the input power. The pump efficiency of 72.1% was taken directly from a well-known manufacturer's curve for a base-mounted end-suction centrifugal pump, and we've assumed all pumps are using premium efficiency motors at 95%. Now that we know we need 55.3 horsepower of input power, we then convert from horsepower to kilowatts. As you can see, our main pump requires 41.2 kW to move the water around the loop. Next, let's take a look at the boiler pumps. Each boiler pump will move half of the total system GPM because, of course, the system is designed to run 2 boilers to meet the load. The same calculations apply, and using a pump efficiency of 45.9%, we arrive at 9.1 kW needed for each boiler pump. So, to sum up, we require a total of 59.4 kW to run the main loop pump and the 2 boiler pumps. If we assume that these pumps will run all year, 8,760 hours, and that our cost for a kilowatt hour of electricity is 10 cents, you can see that just running the pumps costs over $52,000 a year. And there's another cost. Producing that electricity impacts the facility's carbon footprint. The average amount of carbon released to produce 1 kilowatt hour of electricity is 0.818 pounds, meaning our hydronic system emits over 212 tons of carbon each year. So what if we use steam instead of hot water in our system? Let's begin with some steam parameters. For our example, we'll assume we're using steam at 100 psig, a very typical pressure supplied by a central plant. As we explained in our video on the high-efficiency closed-loop steam system, we want to return our condensate at low temperature to achieve maximum efficiency. For this example, we'll assume 130-degree condensate. Now that we know our steam pressure and condensate temperature, let's take a look at the properties of our system and calculate how much energy we can move with that steam. If we look at the saturated steam tables, we'll find that 100 psi steam contains 880 BTUs per pound of latent heat energy. If we condense that steam and then cool it to 130 degrees Fahrenheit in our Maxi-Therm heat exchanger, we can extract another 208 BTU per pound of steam in the form of sensible energy, because the saturation temperature of 100-pound steam is 338 degrees. By cooling it down 208 more degrees to 130, that's where we get our 208 additional BTUs per pound. Therefore, the total energy available in each pound of steam in our 100 psi example system is 1,088 BTU. Remember that value for the next slide. Now let's see how many pounds of steam it will take to produce our design output. Here we're going to figure out how many pounds per hour of steam we'll need and how much condensate that'll produce. Here's the energy that we calculated would be available in our 100-pound steam condensed and cooled to 130 degrees. In order to produce our design output of 35,140,000 BTU an hour, we take that value and divide it by the BTU per pound of steam, and we can see that we'll need 32,297.79 pounds per hour of steam. If we take that mass flow rate and do the same calculations as we did earlier when we looked at our hydronic pumps, you can see that we will generate 65 GPM of condensate. Although it's nowhere near the amount necessary for our example hydronic system, we will need a little bit of pumping energy in our steam system to push feed water back into the boilers. Let's take a look at that and compare the two systems. Remember that 65 GPM of condensate? That condensate was produced from steam that was made from 65 GPM of boiler feed water. It's also very important to remember that since we're using Maxi-Therm vertical flooded heat exchangers in our system and we'll be bringing the full 100-pound steam pressure to those units, there will be plenty of pressure to push the condensate back to the boiler feed unit without pumping it. So the only pumps we need for our system are the boiler feed pumps. Since we're entering a 100 psi steam boiler, we chose the operating point for our feed pumps to be 33 GPM each at 277 feet of head, which is a 120 psi boost. We then sized our pumps to be able to provide a surge flow of 41 GPM, and looking at a well-known manufacturer's curve for a multi-stage vertical pump capable of that performance, but operating at only 33 GPM on average, we determined that the pump efficiency would be 64.4%. Plugging that into the same calculations we used before, we determined that our feed pumps each require 2.82 kilowatts to feed water to the boiler, or 5.64 kW for both. Again, assuming 10 cents per kilowatt hour, those pumps will cost $4,941 a year to run continuously. If we subtract that cost from the cost to run the pumps in the hydronic system, you can see that we will achieve an overall pump energy cost savings of over $47,000 a year. That also reduces the carbon footprint by 192.6 tons per year. Now let's take a look at our main piping loop. Let's look at the piping requirements for our example hydronic system and a steam system designed to deliver the same amount of energy. You'll remember from our earlier calculations that the main piping loop for our hydronic system requires 937 GPM of flow. In order to handle that flow rate, we would use 10-inch supply and return piping. Now let's take a look at our steam system. To transport our design heat load, we'll need 32,298 pounds per hour of steam and 65 GPM of condensate. As you can see, we end up with an 8-inch steam supply pipe and a 2.5-inch condensate return pipe, quite a bit smaller. This smaller piping will certainly cost less to purchase and install, and as we'll see in the next slide, our piping system will also lose less radiant heat. According to ASHRAE Standard 90.1, there are minimum thicknesses of insulation that must be applied to mechanical piping systems, depending on the temperature of the fluid in the pipe as well as its diameter. For our hydronic system, the standard calls for 3-inch thick insulation on the 240-degree supply pipe and 2-inch thick insulation on the return pipe. Calculating the heat transfer through fiberglass insulation, we determined that the combined heat loss in this system for 1 foot of supply combined with 1 foot of return piping came out to 96.5 BTU per hour. We've assumed that all insulation has an all-service jacket and the piping is all installed so that it is not affected by wind. Next, we looked at the steam system, and for these pipes, the standard calls for 4.5-inch thick insulation on the 338-degree steam line and 1.5-inch thick on the condensate return line. Using the same assumption as the hydronic insulation, we calculated that the combined heat loss for 1 foot of steam pipe plus 1 foot of condensate return pipe will be 72.9 BTU an hour. So, the hydronic system will have 32.4% more energy loss from the piping than our steam system. As we've discussed, using steam instead of hot water has some cost-saving advantages, but reduced pumping energy and less piping losses are just the beginning. The biggest advantage to using steam happens when we implement the high-efficiency closed-loop system using Maxi-Therm vertical flooded heat exchangers. The cool condensate they can produce allows us to achieve 95% efficiency from our main steam plant, as discussed in our other video. Let's summarize the cost savings we can enjoy by using steam. Let's take a look at the savings we can achieve by using steam instead of a hydronic system. First, let's look at natural gas costs, starting with our example system and its 85% efficient hot water boilers. To achieve our design output, we need an input of 41,340,000 BTU an hour. Compare that to our steam system at 95% efficiency, which only requires a little less than 37 million BTU an hour input. That equates to an annual savings of $381,235 a year, assuming gas costs $1 a therm. To see what savings we can achieve due to smaller radiant heat losses from our smaller piping system, let's assume a total loop length of 4,000 feet, 2,000 feet out for the supply and 2,000 feet back for the return or condensate piping. In our high-temperature hot water system, we would lose 19,890 therms per year, and in our steam system, we would only lose 13,444 therms a year. That would result in a cost savings of $6,446 a year. The last component of savings is pumping energy. To recap, the hydronic system uses $52,034 in electricity to move water around the loop, and our steam system only needs $4,941 to operate the boiler feed pumps. That cost savings is over $47,000 a year. Add it all up, and you can see we can achieve over $430,000 a year in savings every year by using steam and Maxi-Therm vertical flooded heat exchangers instead of hydronic heating. And that doesn't take into consideration any installation cost reductions achieved by using smaller piping in our main loop. But we're not just saving money here. We're also saving the planet by reducing our carbon footprint. Each of the cost savings we showed on the previous slide comes from a reduction in energy usage. Now let's quantify how much carbon footprint reduction comes with those savings. Of course, the big one is the savings we achieved by making our steam plant 95% efficient. That represents savings of 381,235 therms of natural gas each year. At 12.12 pounds of carbon produced per therm of gas consumed, we are avoiding the creation of 2,310 tons of carbon each year. Also, because we're losing less energy in our piping system, we save another 6,446 therms of gas each year, which reduces our carbon footprint by another 39 tons. Looking at pumping energy, our steam system uses almost 471,000 fewer kilowatt hours per year. The average carbon emission from producing electricity is 0.818 pounds of carbon per kilowatt hour, So our system saves another 193 tons of carbon emissions each year due to reduced electricity usage. It's quite an impressive total carbon footprint reduction, over 2,500 tons every single year. I think we've shown you that steam is more efficient than you might have thought, and we believe it's a technology for the future, not just the past. Steam provides a path to cost savings and decarbonization. That concludes our presentation on hydronic versus steam, and we think you'll agree, steam wins.